Hi, thank you for everyone for being here. My name is Patrick Roberts,
I am Benjamin Alu.
and this is our senior project presentation for the Smart Electric Skateboard. So, getting into it, here's what we'll cover in this presentation today. We'll go over the project overview and research, the project components and allocation, project objectives, system block diagram, basic assembly, and then modification. So, starting off, why is a smart electric skateboard necessary? So, one of the problems with current electric skateboards today is they offer no user capability, no increased functionality, such as like a cruise control system or LEDs to indicate turn signals or whatnot. So a smart electric skateboard is something that incorporates this functionality with increases in safety, a user-friendly system. It incorporates creature comforts like like a cruise control. It's user configurable, and so that's kind of why we got into this project. So some of the research that also shows that this is necessary is, for one, cruise control, which is a big component of this project, actually increases adherence to speed limits. So you don't concentrate on your throttle so much as you're riding. And also we are implementing a smart LED system, which we'll cover later in the project. But those, it's proven that LEDs, improve rider visibility and allow vehicles to see you from farther distances. And then also some statistics of some injuries and deaths that have been recorded on current, electric scooters or electric skateboards. One study in Copenhagen showed that there were 468 deaths, and Atlanta has actually banned all nighttime scooter riding or electric scooter riding. So our project aims to, cut down on injuries and cut down on fatalities with some of these features that we'll show. So these are the seven features, or the seven features that we are implementing and how are they allocated, and Ben will go into that slide.
Okay, so like the project components and allocation, we have the cruise control, Patrick, Brad, and myself, and smart LEDs. Brad has taken the lead on that since he has a lot of FPGA experience. At the LCD touchscreen, Brad has also taken initiative with. Initially, he got it to work some with the TI board, and then when we switched to the Mega, and then the Bluetooth capability, Patrick and Jordan handled that part of the project. The strain gauge, David covered. And battery monitoring system, initially it was Mark, but then Patrick and I stepped in and helped out. We all got that pretty much figured out. And then the machining hardware and design mechanical component I handled. And so then moving on to project objectives, we have the implementation of smart LEDs to not only increase the rider visibility, but to show braking and moving actions like a turn signal, or if there's an emergency, say if there's a crash, then it could a hill or something, the rider can indicate through blinking mode. Cruise control, of course, is imperative, and the configurable smart controller, so it can read battery life, distance monitoring, current speed, and even a recent added feature completed by Brad. We have added a safety, like a pin, security pin, and then a rider detection system to determine if the rider is on or off of the board, so it won't just keep going if the rider falls off of it. And here's the system block diagram that Patrick's going to take over.
Okay, and then just to briefly go into the system block diagram, you'll see in the middle, or the two microcontrollers selected for this project were the ATmega 2560. One will be mounted into a hand controller, one will be mounted into the actual board itself, and they will communicate via Bluetooth. And the board controller will control the speed of the motor via an electronic speed controller, and the hand controller will receive speed data and throttle data and display that on the LCD screen, as well as configure the smart LEDs that will be mounted around the skateboard itself. And so we'll go on to board assembly, which was Ben's part of the project.
Okay, so board assembly was pretty straightforward for the most part, basically just swapping out the hardware like the trucks and the wheels and all that. We did run into a little bit of issues, however, when trying to install the belt drive. It was slightly smaller than the truck because they all came from different parts, so that is where we get into the hardware modification, where I had to take a little bit of material off of the drive pulley, and also the video is not shown here, but ended up having to mill, as you can see by the picture, mill a section of the truck so that the belt could clear, and we were able to scoot the motor bracket back just far enough. And then you can see the the board layout. It's been difficult with the pandemic, or given the pandemic situation, to actually meet up regularly and do actual hardware assembly. But this is how the layout would be, with the battery pack positioned furthest away from the motor. That way it would have even weight distribution. The FPGA block is nestled in between our Mega controller for the board and our ESC. And the hand controller is going to be, that's going to be another slide. And the lights would go around on the outside of the board. And then the Bluetooth module, you can see it on top of the ESC. And then Patrick will show how we tested a PWM run with our board.
Right, and so in this video, all we did was connect a potentiometer to the microcontroller, which fed a analog signal to it. And then via the potentiometer, we could control the speed of the motor by the varying PWM signal that you can kind of see on the oscilloscope. And then finally, that wraps it up, and this is our bibliography. So thank you so much, and the other videos for our group members will play now as well. So thank you so much.
Thank you.
For the electric skateboard, the group desired to have a safety feature that indicates and responds to when a rider mounts or dismounts the board. Therefore, the group decided to go along with the strain gauge. The strain gauge is like a variable resistor. When tension or compression is applied, the resistance of the strain gauge increases or decreases, but only at a very small amount. Therefore, we utilize a Wheatstone bridge circuit and also a 24-bit analog to digital converter to account for the small changes. Also, rather than using 3 series resistors to add up for 350 to match for the strain gauge resistance, I decided to go along with the trimmer potentiometers, where I can calibrate each potentiometer to each strain gauge, because when strain gauges are applied to this material, they don't come out to exactly be 350. In order to calibrate each potentiometer, first I must measure each strain gauge. After applying each strain gauge to the wooden material, the resistance of each changed slightly. Therefore, using a 350 ohm resistor or a feed resistor to add up to the 350 ohms would not properly work. Therefore, I used a voltage divider with an analog reading in between to read the output of how many volts coming out and then calibrate it into the way where I can read resistance. I used the strain gauges as my reference resistors and then matched the potentiometer with it. Therefore, they both will have exactly the same resistance inside the circuit. Here, the group presents the final strain gauge circuit. At the bottom of figure 3, you can see the 2 strain gauges attached to the wooden beam. In the middle, you have the 2 blue boxes, which are the potentiometers. And at the top, you can see the 24-bit ADC. The ADC amplifies the output voltages in between the potentiometers and the strain gauges. But the output voltages from there needs to be converted back into the range of 0 to 5 volts. Once the rider is off the board, there's no applied force. Therefore, the voltage is above the determined threshold, which is shown in figure 4 of the serial monitor. In figure 5, the applied force onto the beam, the output voltage went below the threshold that was determined. Therefore, it shows that the rider is on.
My name is Jordan McGuire, and I was over the wireless communication portion of the Smart Electric Skateboard project. My primary goal was to get the microcontroller and the hand remote communicating with the microcontroller located in the Smart Electric Skateboard. Although Zigbee was originally chosen for communication between the 2 microcontrollers, Bluetooth was finally decided upon because of its higher speeds and ease of use. The components used in completing this portion of the project are shown on the right. Located on the bottom left of the group is the HC05 Bluetooth module required for Bluetooth communication between the 2 microcontrollers. At the top is a TI Launchpad. The TI Launchpads were the first microcontrollers that the Bluetooth communication was attempted on. Wireless communication was never successfully completed with the TI Launchpad boards due to overheating issues. Our last resort was to use the Arduino Uno. Using the Arduino Uno, we were able to successfully communicate wirelessly between the 2 boards. Before serial communication was possible, the Bluetooth modules had to be set up so that they could pair properly. This setup is done in AT command mode. The schematic for AT command mode is shown on the left, and the AT commands are shown on the right. In AT command mode, the role of the master and slave are assigned to each of the Bluetooth modules. When the setup is completed successfully, whenever turned on, the two Bluetooth modules will recognize each other and will automatically pair. This slide shows the circuit built to test simple serial communication between the two microcontrollers. Each of the circuits are set up with an LED and a push button. When a button is pressed in one circuit, a serial 1 is transmitted via the Bluetooth module to the other Bluetooth module and microcontroller, which reads the serial 1 and turns on the LED. Here is a video of the Bluetooth test. This is the microcontroller that will be transmitting. Here's the push button, and in this case, both LEDs will light up when the button is pressed. Here's the side that's receiving the serial data, and as you can see, the LED is successfully lit, and it turns off when the push button is released.
So here I'm going to talk about the battery monitoring system of the electric skateboard. So the circuit was designed so we could display the current or existing life of our battery on an LCD, and this will be displayed as a percentage. So our circuit has an input voltage of 33.6 volts, which is basically all of our combined battery cells in series, and we wanted to step that down so that we can get an output of 4.5 volts from our op amp. So for example, let's say the battery, which is at our desired 4.5 volts, is at 4.5 volts, you'll have 100% battery life. Let's say your desired battery life is actually at 2.25 volts, then your battery life is at 50%, and so on and so forth. Also, the objective of this is to find out the current draw from the load of the motor and the 0.02 ohm resistor. All of that's going to be displayed on the LCD. We don't know what the current value is going to be, and we won't really find that out. The true current value, at least, we won't find that out until we have this number displayed on our LCD. And we want to know what that behavior is going to be over time as the battery life decreases over time. Here we have two circuit schematics. And the difference of these schematics is this circuit on the left. We have the 0.02 resistor in R3 right here. This is our 0.02 resistor, and this is basically 5.1 ohm resistors in parallel with each other, and that gives that out to an equivalent resistance of 0.02. So based off this design, we wanted an output of 4.5 volts, and from there we actually found out what our resistor values were going to be. So here, based off all of that, you can see here in the table below on the top left that we actually have an output voltage of approximately 4.5. And then the circuit on the right was just our first simulation that we did, and that was before we implemented the 0.02 ohms. And then here is the LCD battery actually working. So unfortunately, my microcontroller shorted when I finished the code for the current display, and due to COVID-19, I could not order a new microcontroller. But the whole purpose was to find out what the current is from our loads, and then we also have our desired percentage values at its existing or current state.
Oh, hi! I didn't see you there. I'm Brad Jackson. You know, this project has been an incredible journey for me. I would like to share with you my experiences in this project. I focused on the embedded systems aspect of the project. To make the skateboard smart, we knew we needed a powerful way for the user to interface with the skateboard, wireless communication a necessity, safety systems such as lighting and a strain gauge to monitor whether the rider has fallen off, as well as battery monitoring systems and a way for the user to know how fast they're going. Well, this is quite the laundry list. So I decided early on we would use an FPGA, a field programmable gate array, as a way to offload the many cycles it would require to light the LEDs. The smart LEDs require precise timings, and by moving them to the FPGA, we save millions of cycles on the embedded system aboard the skateboard. Now, challenges emerged early on. Wireless communication proved elusive, the touchscreen refused to run at the correct speed, the Hall sensors used to monitor the speed wouldn't cooperate. COVID-19 scattered the team, and with them the components. The full view of the project became obscured. We, however, persevered. I incorporated the security system, the touchscreen, a way to monitor and control your speed, set cruise control, and a lighting system to provide safety and versatility to the rider. I would like to present this project to you now.
Welcome to my demonstration of features I have implemented into the project. Utilizing a 2.8-inch capacitive touchscreen, the Smart Skateboard features a password security system. The system will not start until the correct 4-digit PIN is entered. The user is then greeted with the startup screen. Here is the user interface I have designed. Users can view their current throttle settings at the top, and via the touchscreen, users can toggle cruise control, adjust the throttle, and choose from one of 4 different lighting modes. A potentiometer is used to simulate the trigger built into the hand controller that controls the speed of the motor. This demonstrates the cruise control functionality of the system. By enabling cruise control, users can manually set and adjust the throttle using the touchscreen. The Smart Skateboard is equipped with 4 lighting modes: a left blinker, a right blinker, flashers for emergency use, and a well-lit default drive mode that provides illumination and tail lights. This is all made possible by a strand of 60 smart LEDs controlled by a Xilinx Basis 3 FPGA. Thank you for watching.